We can easily see how the polarity or asymmetry of distribution of electrons in one molecule can affect a group of molecules in experiment 64, which is the attraction between water molecules. On the left here, we have a sample, effectively a little universe of ourselves with just two water molecules existing in a vacuum. And I'm going to visualize the distribution of the electrons of this sample in two different ways. The first way I'm going to visualize it is I'm going to move the molecules apart just a little bit and look at the polarity maps. And we can see from the polarity map, which represents the distribution of the electrons in the molecule, we can see that the oxygen side of the molecule is represented in red, while the hydrogen side of the molecule is represented in blue, which is trying to tell us effectively that the distribution of the electrons in the water molecule of a whole is skewed to the oxygen side relative to the hydrogen side, which is making the oxygen side effectively more negative than the hydrogen side of the molecule. Now, whereas quantum mechanics is the only way that we can make these three-dimensional visualizations of polarity, we can go back to a more classical representation of this property of water by looking at the dipole arrow. So if I pull the dipole arrow in here, we see an arrow that basically is struck through the heart of the oxygen atom, with the head being close to oxygen and the tail being near the hydrogens, going with the standard IUPAC definition that the head of the arrow represents the negative side of the molecule and the tail represents the positive side. And we see right away here with these two water molecules, the negative side of one molecule is aligned up with the positive side of another water molecule from right here. And let's initiate an actual simulation of the model of the two going around here. And what we can see is the two water molecules run around one another, that it's true that if we look at any distribution of the two water molecules for no matter how long we run the sample, the interactions of the molecules are one is perturbed by the other, meaning that as one water molecule rotates and chooses its or orients its positive and negative side in different orientations in space, the other molecule follows suit, so that we will see that for any particular orientation, that the head of one dipole arrow is effectively close to the tail of a subsequent dipole arrow. We will never see at standard temperatures two dipole heads interact with one another because of the repulsive features of either the two negative or positive sides of the molecule. So therefore, once we have localized polarity on each water molecule and put two water molecules together, we will see right away that they will dance together in a group such that interactions are maximized, such that potential energy is minimized, and that the head of one arrow, the negative side of one molecule, is always oriented relative to the positive side of another molecule. Now, this is true for the water dimer, but it's also true if we look at molecules beyond the water dimer. What if we were to add, for example, 10 water molecules as opposed to 2? So in order to do that, we're going to go to the Properties menu and view some properties of the system. And one of the things we're going to do is change the total number of molecules. So I'm going to go to System, Total Number of Molecules. We notice that a slider comes up for us that allows us to dynamically change those molecules. We can select the number, we can slide the bar or select the number. I'm just going to select the number and increase the number of water molecules to 10. And what this has done now is that we have randomly added to our little universe 10 water molecules themselves. And we'll notice, since they were randomly added now, that it's true that we may see some dipole heads close to one another or some dipole tails close to one another too. For example, if we look right here, with these two water molecules, you can see these two heads are relatively close to one another. That's because the system has been added randomly. We've just thrown some extra water molecules into the volume without any regard for the orientation of the system. So what we're going to do to bring some regard to the orientation of the system is we're going to minimize the total potential energy of the system from right here, and we're going to let Odyssey explore various orientations of the water molecules to find the potential energy minimum for the system here. And there are two ways to do that. We can go to the minimize button right here, which is what I'm going to do, or we could go to the build menu and hit minimize there too. Either way will minimize the system. I prefer to use the button, so we'll do that right there. And what now Odyssey is doing is it's performing multiple calculations to find the orientation of the water molecules so that they are at the lowest possible potential energy state. And we see right here with this minimization, and you can keep minimizing multiple times, we see right here that interestingly in this case it looks like we formed two different rings. And we see within the context of these rings that the dipole heads and the dipole tails, and not surprisingly, are lined up effectively head to head. Now let's watch the dynamics of this system, and in order to properly utilize Newton's second law here, we're going to turn down the time step. So we're going to go to dynamics and time step. This is going to allow us to do our integrations properly so we don't see any strange motion just by running the system too quickly. And we're going to lower it to 0.05 femtoseconds. And now let's just visualize the system and watch what happens. So now instead of having the 2 atoms from before, we see that we have now this 10 atom system. And in this 10 atom system, there are changes in configuration. It's now almost like we're now making, instead of 2 small rings, almost 1 large ring. But notice that no matter how the system runs, we are always seeing a scenario where the head of one dipole arrow is lined up directly with the tail of another. So therefore, these ring-like structures that we form are just a natural consequence of the interactions of the positive and negative sides of individual water molecules. And they morph, they change, and every once in a while we may see an individual molecule get thrown off or affected slightly, like we're seeing this one up here, just because of the natural motions of the system. But the system is always going to try and find that configuration that allows us to put the water molecules as much as possible tip to tail, because only in that configuration can we minimize the potential energy or maximize the attraction of the system from right there. If we were to build another system, we would see a slightly different configuration, but the structure of the group itself is completely dictated by both the kinetic energy of the molecules, how much energy they have right now, and more importantly, the attractive forces between them in real time. So getting the structure of solids and liquids is no more of a task than just figuring out how do the interactive forces relate from one molecule to another. How do 2 or more molecules interact in such a way to try and come up with a lowest possible energy configuration for a given temperature?